Make your search results much more accurate with re-ranking. By the end, you will have a tiny pipeline that goes from keyword filtering to learned re-ranking. You will see how a simple overlap filter and Jaccard pre-selection feed a compact cross-encoder that improves ordering at the top. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Why this matters. Good search is not just matching words. It is ordering results so users find what they want fast. Re-ranking optimizes ranking quality measured by NDCG, which scores how useful the top of a list is by weighting higher positions more. The trade-off is CPU and latency, because a cross-encoder reads query and document together and is heavier than an embedding lookup. In practice, re-ranking over a few candidate documents often lifts top precision noticeably without enormous cost. Conceptually, think of two stages. First, a cheap filter finds plausible documents using word overlap or set similarity. Then a cross-encoder reads each query with each candidate, and it learns subtle signals like phrase match, negation, and context. It shines when you need precise ordering in the top results. It limits you by compute, so you use it on a short candidate list rather than the whole corpus. We will build a small end-to-end demo. It filters with simple token overlap, then scores with Jaccard, then builds query document pairs, then re-ranks with a pre-trained cross-encoder, and finally shows a full baseline re-rank. Now we start with a basic keyword filter. This snippet ranks toy documents by simple keyword overlap with a query. It defines a tiny corpus and a short query, then tokenizes the query into lowercase words using a regular expression to make matching consistent. The variable QW is a set of query words for fast membership checks. For each document, the code counts how many query words appear and pairs that count with the document text. It sorts by highest score and breaks ties alphabetically to keep the result stable. The printed tuples show the top matches and how many query words each document contains, making the ranking transparent. Next, we make the matching a bit smarter by measuring set overlap proportion. This snippet scores documents using Jaccard similarity to weight partial matches. It reuses the same corpus and query, turning the query into a set of tokens named JW. For each document, it forms a set of its tokens and computes the ratio of intersection size to union size, capturing how much the sets overlap relative to their combined vocabulary. The list SC pairs each score with the document, then sorting preserves stability while selecting the top two. Scores are rounded to 2 decimals for readability. The printed floats show the proportion of shared tokens that drives the ranking. Next, we prepare the exact input shape a cross-encoder expects by pairing query and document text. This snippet builds query document candidate pairs for cross-encoder re-ranking. It takes the top documents from the previous Jaccard step using K as the number of candidates to keep. The variable cans holds those document texts in order. The list pairs then couples the same query with each candidate document, creating the exact 2 text inputs a cross-encoder expects. Increasing K broadens recall, but adds compute because the model scores more items. Decreasing K speeds things up at the risk of missing good results. The printed pairs confirm the batched inputs that will be scored next. Next, we hand those pairs to a pre-trained cross-encoder to get learned relevant scores. This snippet re-ranks the candidate pairs with a pre-trained cross-encoder model. It loads a compact cross-encoder that reads the query and document together and learns to score relevance directly. The predict function returns a score per pair, where higher means more relevant. Zipping scores with the original documents. It sorts in descending order to get the model's preferred sequence. Only the document texts are printed to keep the output short and deterministic. The printed list shows the cross-encoder's ordering of the candidates, reflecting learned relevance beyond simple token overlap. Finally, we contrast pre-selection with scoring the whole corpus for a baseline. This snippet applies the cross-encoder to all documents for a small baseline. It forms pairs for every document, scores them with the same CE model, and sorts by score so the best matches come first. Unlike pre-selection, this evaluates the entire corpus, trading more compute for potentially higher recall and better final ranking. The code then prints the top 3 results as a compact, user-ready list. The printed order is a complete re-ranked set, serving as a tiny end-to-end search baseline. Recap. What it is: a 2-stage pipeline that uses a cheap filter or Jaccard pre-selection and then a cross-encoder for precise ranking. When to use it: when you care most about the top of the list and can afford a little extra compute on a small candidate set. One caveat: the cross-encoder is powerful but slower, so pick your candidate size carefully. Next step: try increasing the candidate size K and measure top 3 accuracy and latency. If you need more scale, swap the pre-selection to an approximate nearest neighbor stage and tune the candidate size accordingly. If practical, short IR improvements help real users. Subscribe and watch the other IR videos for benchmarks and extensions.